The CAP Theorem explained. Navigating consistency, availability, and partition tolerance in distributed systems. Chapter 1, Introduction. The Unseen Orchestra of Distributed Systems. 1.1, Welcome to the Distributed World. Pause for a moment and consider a typical day. You might wake up and check your smartphone for new messages or social media updates. Later, you'll probably order a coffee using a mobile app, pay for groceries with a digital wallet, or stream your favorite show online. Perhaps you're even reading this book on an e-reader or listening to it through an audio service. What do all these seemingly simple, everyday actions have in common? They are powered by an invisible, sprawling network of computers working together across vast distances. You don't interact with a single, monolithic machine. Instead, your request is sent to a colossal orchestra of servers, databases, and specialized services, all communicating rapidly to fulfill your immediate need. This intricate web is what we call a distributed system. Imagine trying to book a flight. In the blink of an eye, the system checks seat availability across multiple airlines, calculates fares, verifies your payment, updates the airline's internal records, and sends you a confirmation email. Each of these steps might involve different computers, perhaps even in different continents, all needing to cooperate seamlessly to complete a single transaction. It's like a meticulously coordinated symphony, where every instrument, a computer or service, plays its part, perfectly in sync, to produce a harmonious outcome for you, the user. To fully grasp the sophistication of this arrangement, it helps to contrast it with what came before. For many years, computer systems were primarily centralized. Think of a single, powerful mainframe computer in a basement, handling all computations and data storage for an entire organization. If that one computer went down, everything stopped. If it got overwhelmed with too many users, the whole system slowed to a crawl. It was like a solo performer trying to play every instrument in an orchestra by themselves, powerful but limited in scale and vulnerable to a single point of failure. Today, that centralized model is largely a relic for large-scale operations. The demands of millions, even billions, of users interacting concurrently, coupled with the need for constant availability and instant responses, made the single-server approach unsustainable. The age of the distributed system was born out of necessity. 1.2, The allure and agony of going distributed. So, why did we choose this path of complexity? Why break down a perfectly good single-server system into countless interconnected pieces? The reasons are compelling, driven by the relentless march of technological progress and user expectation. Scalability. This is perhaps the most significant driver. A single computer, no matter how powerful, has limits. A distributed system, however, can scale almost infinitely. Need to handle more users? Add more servers. Need to store more data? Add more storage nodes. It's like adding more musicians to the orchestra. You can grow its capacity to perform increasingly complex pieces for a larger audience. Reliability and fault tolerance. In a centralized system, a single component failure means the entire system fails. In a distributed system, if one server goes down, others can often pick up the slack. Data is replicated across multiple machines, so if one copy is lost, others remain available. This enhances the system's resilience, its ability to endure failures without disrupting service. It's the difference between a solo musician getting sick and the entire orchestra having understudies who can step in. Performance. Spreading the workload across many machines can significantly improve response times. Requests can be routed to the closest server, or complex tasks can be broken down and processed in parallel. This means faster load times, quicker transactions, and a smoother user experience. The allure of these benefits is undeniable. Distributed systems underpin virtually everything we do online, from searching for information on Google to streaming movies on Netflix. However, this power comes at a price: the agony. As with any complex endeavor, managing a distributed system introduces a new class of challenges that are far more difficult than those found in a single-server environment. Complexity. Coordinating hundreds or thousands of independent computers is inherently more complex than managing one. Data must be consistent across multiple locations, messages must be delivered reliably, and failures need to be handled gracefully. This leads to intricate software architectures and operational overhead. Coordination challenges. How do all these independent machines agree on the true state of affairs? If two users try to buy the last item in stock at the exact same moment, how does the system ensure only one succeeds and the inventory count is accurate? This is a fundamental problem of consensus. Network unreliability. The internet, for all its marvels, is not perfectly reliable. Messages can be delayed, duplicated, or lost entirely. Computers can disconnect from each other without warning, creating partitions where parts of the system can't communicate. This unpredictable behavior of the network is an ongoing source of headaches for distributed system designers. Debugging and monitoring. When something goes wrong in a single server, you check that server. When an error occurs in a distributed system, it could be anywhere, affecting any number of components. Pinpointing the root cause can be like finding a needle in a haystack of needles. These challenges aren't theoretical. They are daily realities for engineers building and maintaining these systems. They force fundamental questions about how to design systems that are both powerful and resilient, while still providing a coherent experience to the user. 1.3 The core dilemma. When systems go rogue. Let's zoom in on one of the most insidious problems: partial failure. In a single, centralized system, a failure usually means the whole system is down. It's binary. Either it works or it doesn't. In a distributed system, individual components can fail while others continue to operate. This creates a highly confusing and dangerous situation. Some parts of your system might think everything is fine, while others are struggling or completely isolated. Consider a scenario where you're trying to view your bank balance. Your request might go to one server, which then queries a database. That database, in turn, might be replicated across several machines in different data centers for reliability. What happens if the network connection between two of those data centers suddenly breaks? One part of the system might now be isolated from another. Let's say you have $100 in your account. You try to transfer $50. Your request goes to a server, which updates its local copy of your balance to $50. But because of the network break, it can't tell the other data center about this update. If you then try to withdraw $70 from an ATM connected to the other data center, it might still think you have $100 and allow the transaction, potentially leading to a negative balance. This is where the system has gone rogue. It's no longer presenting a consistent view of reality. This isn't just about network splits. It could be a server slowing down, a disk failing, or even a temporary glitch in a router. The unpredictable nature of these failures means that distributed systems regularly face situations where parts of the system are unable to communicate with other parts. How do you respond to this? Do you halt all operations until the network is fully restored, potentially making your system unavailable? Or do you allow operations to continue, risking inconsistent data across different locations? This, ultimately, is the central dilemma that lies at the heart of designing distributed systems. It's a problem so fundamental and far-reaching that a pivotal idea emerged to help us navigate it. 1.4 Enter the CAP Theorem, a guiding star. It was in 2000 that Eric Brewer, a computer scientist at the University of California, Berkeley, articulated this fundamental constraint at a symposium. His insight, which later became known as the CAP Theorem, provided a clear framework for understanding the trade-offs inherent in distributed systems design. The CAP theorem states that a distributed data store can only guarantee 2 out of 3 desirable properties simultaneously during a network partition. Consistency, C. Every read receives the most recent write or an error. It's about ensuring that all clients see the same data at the same time, regardless of which node they connect to. It implies a single, up-to-date view of the data across the system. Availability, A. Every request receives a non-error response without guarantee that it contains the most recent write. It means the system remains responsive and operational even if some nodes fail. Partition tolerance, P. The system continues to operate despite arbitrary message loss or failure of parts of the system. This means the system can tolerate network partitions, situations where communication between parts of the system is disrupted. The theorem part implies that in the presence of a network partition, P, you must choose between C or A. You cannot have all three at the same time. It's an unavoidable truth of the distributed world. Think of it like a three-legged stool. Consistency, availability, and partition tolerance are its legs. The CAP theorem says that if one leg, P, a network partition, is compromised, you can only pick one of the remaining two, C or A, to prioritize without falling over. You either ensure everyone sees the same information, C, at the cost of sometimes being unable to respond, A, or you always respond, A, even if the information might temporarily be out of sync, sacrificing C. The P, or partition tolerance, is often assumed as a given in most real-world distributed systems because networks will fail. This isn't about what you can't do, but rather about the fundamental choice you must make when your network divides. It forces designers to actively decide which property is most critical for their application, strict data accuracy, or uninterrupted service. This book will embark on a journey to demystify the CAP theorem, breaking down each of its components, exploring how different real-world systems make these fundamental choices, and showing you the practical implications for designing robust, scalable, and resilient distributed applications. By the end, you'll not only understand the CAP theorem, but also appreciate why it serves as a guiding star for anyone navigating the complex, unseen orchestra of distributed systems. Let's begin by deeply understanding each of its core concepts. Chapter 2, Foundational Concepts. What even is a distributed system? Before we delve deeper into the intricacies of the CAP theorem, it's crucial to establish a common language and understanding of the fundamental building blocks that constitute a distributed system. While we've already painted a broad picture, truly understanding the CAP choices requires a firm grasp of the underlying architecture. 2.1 The building blocks. Nodes and networks. At its simplest, a distributed system is a collection of independent computers that appear to its users as a single, coherent system. To make this happen, we need two primary components. Nodes. These are the individual computers within the system. You can think of them as the individual musicians in our orchestra. A node can be a physical server, a virtual machine, a container, or even a smartphone. Each node has its own processing power, memory, and storage. In a distributed system, nodes typically communicate with each other to achieve a common goal. For applications like a social media platform, one node might handle user logins, another might store profile pictures, and many others might hold snippets of news feeds. Each plays a specialized or generalized role. Networks. If nodes are the musicians, the network is the airwaves or the stage, the medium through which they communicate. Networks connect nodes, allowing them to exchange data, instructions, and messages. This communication can happen over local area networks, LANs, within a data center, or across wide area networks, WANs, like the Internet, spanning continents. The reliability and speed of this network are paramount, as the entire system depends on the ability of its nodes to converse. Just as a conductor relies on hearing every instrument, nodes rely on their ability to send and receive messages. Imagine a large library system that wants to offer its catalog online. Instead of one giant computer storing every book record, they might distribute the workload. One computer node could handle user accounts, another could manage the database of digital books, and yet another could serve the website. These nodes would be connected by the library's internal network. When you search for a book, your request travels across the network to the web server, which then, through the network, asks the database server for the information. 2.2 Data everywhere. Replication and distribution. One of the cornerstones of distributed systems is how they manage and store data. It's rare for all data to reside on a single node. Instead, data is almost always distributed across multiple nodes for several critical reasons. Scalability. If a single database server handled all of Facebook's data, it would quickly become a bottleneck. By distributing data, we can spread the storage and processing load across many machines. This is often done through a technique called sharding, where the database is divided into smaller, manageable chunks, shards, and each shard is hosted on a different node. For example, users with names AM might be on one server and NZ on another. Reliability, redundancy. What happens if a node holding critical data fails? If there's only one copy, that data is lost or inaccessible. To prevent this, data is often replicated. This means identical copies of the data are stored on multiple nodes. If one node fails, another node with a copy of the data can take over. This is like having multiple copies of an important document stored in different fireproof safes. If one safe is destroyed, the document is still safe elsewhere. Performance. By replicating data, nodes can sometimes read data from a nearby or less busy replica, reducing latency and speeding up access. If a popular video is stored on servers around the world, users can stream it from the server closest to them, rather than waiting for it to travel across continents. This distribution and replication of data are fundamental to achieving the scalability and reliability benefits of distributed systems. However, it also introduces a massive challenge. How do you ensure that all these copies of data remain consistent and accurate? This tension between having multiple copies and keeping them in sync is a core theme in distributed systems and a direct precursor to the CAP theorem. 2.3 The conversation. Communication between nodes. Nodes in a distributed system are constantly talking to each other. They send requests, share updates, report their status, and acknowledge receipt of information. This communication happens in a variety of ways. Messages. Nodes often communicate by sending messages across the network. These messages can be as simple as, "Hey, are you still there?" or as complex as, "Update this record with this new information." Protocols. Just like humans need language and etiquette to communicate effectively, computers follow specific rules and formats called protocols, e.g., HTTP for web traffic, TCP/IP for network communication. These protocols ensure that messages are understood correctly. Despite the sophistication of these communication methods, the network is not a perfect conduit. Two critical characteristics of network communication profoundly impact distributed system design. Latency. This refers to the delay in communication. It's the time it takes for a message to travel from one node to another. Even on fast networks, latency is never zero. It's an inherent physical limitation. A message sent across a continent takes longer than one sent across a room. This small delay, magnified by hundreds or thousands of interactions, can significantly impact system performance and consistency. Imagine telling your orchestra members to play, but there's a slight, unpredictable delay before the sound reaches each of them. Maintaining perfect rhythm becomes incredibly difficult. Partial failures. This is perhaps the most defining characteristic of distributed systems and the agony we touched upon in Chapter 1. In a network of independent computers, any individual component can fail while others continue to operate. This means node crashes. A server might suddenly stop responding due to a hardware failure, a software bug, or a power outage. Network glitches. Communication links can degrade or break entirely. A router might fail, or a cable might be cut. This can lead to a network partition, where groups of nodes can talk amongst themselves but cannot communicate with other groups. Slow communication. A node might still be alive, but so overwhelmed that it responds too slowly, effectively being as useless as a crashed node. The inability to always know the true state of another node or network connection is a central problem. Did the message reach its destination? Did the other node crash, or is it just very slow? Was my last update received, or is it lost in transit? You can't distinguish between a node that has failed and a node that is merely unreachable. This fundamental uncertainty forces designers to make difficult choices about how their system will behave in the face of these inevitable failures. 2.4 Defining system. The collective brain. When we talk about a distributed system, we're not just talking about a bunch of computers connected by wires. The system refers to the collective intelligence and coordinated actions of these nodes, designed to appear as a single, unified entity to the outside world. From a user's perspective, they're interacting with Facebook or their bank, not with server, us East 1A node 73. The distributed system works tirelessly behind the scenes to abstract away the complexity of its underlying components. It allocates requests, manages data replication, handles failures, and presents a consistent facade. This orchestration relies on sophisticated algorithms and clever design to ensure that, despite the numerous independent parts and the constant threat of partial failure, the whole continues to function as a seamless, high-performing brain. 2.5 What can go wrong? The inevitable failures. We've already touched on it, but it bears repeating. In distributed systems, failure is not an exception, it's an expectation. Any system operating at scale across a network will experience failures. These failures can manifest in various ways. Fail-stop failures. A node simply stops working and does not send any further messages. This is relatively easy to detect. Omission failures. A node fails to send or receive messages. This is trickier, as you don't know if the message was sent but lost or if the recipient crashed. Timing failures. A node produces a response, but it arrives too late to be useful. Byzantine failures. The worst kind of node behaves maliciously or sends arbitrary, incorrect messages. These are very difficult to handle and usually assumed not to happen in most commercial distributed systems, though they are a concern in blockchain technologies, for example. The critical takeaway from this chapter is that networks are unreliable and partial failures are inevitable. Any design for a distributed system must account for these realities. This understanding directly leads us to the core of the CAP theorem. The CAP theorem doesn't just state a theoretical limitation, it provides a framework for managing the consequences of these unavoidable failures. When a network partition occurs, and parts of your system can no longer communicate, you are forced to make a profound choice about how your system will continue to operate. This choice lies at the heart of consistency, availability, and partition tolerance. Chapter 3: Consistency, the illusion of global order. In distributed systems, the concept of consistency can be a bit slippery, carrying different meanings depending on the context. Before we dive into the CAP theorem's specific definition, let's disambiguate and then focus on what consistency means in the context of data seen by users across a distributed network. 3.1 What do we mean by consistent? When most people outside of technology think about consistency in data, they often mean data integrity. For instance, in a traditional database, part of consistency, often called ACID consistency, which we'll briefly cover, means that a transaction either fully completes or completely fails, leaving the database in a valid state. You can't transfer money from one account to another where the money disappears from the source, but never appears in the destination. This is about correctness of the data within a single, atomic operation. However, in the context of the CAP theorem, consistency, C, refers to something more specific. Every read operation returns the most recent write operation or an error. It's about ensuring that all clients see the same data at the same time, regardless of which node they connect to. It implies a single, up-to-date, and coherent view of the data across all participating nodes in the distributed system. Imagine a critical document, say, a company's financial report, being updated by one team member. If another team member pulls up the report minutes later, they must see the updated version, not an old one. Furthermore, if any team member from any office pulls up the report, they must consistently see the exact same, most current version. That's the essence of consistency in the CAP sense. A unified, agreed-upon, and current state of data across all locations. 3.2 The gold standard. Strong consistency. When we guarantee that every read receives the most recent write, or an error if that guarantee cannot be met, we are talking about strong consistency. This is the highest level of consistency and often the most intuitive for users because it mirrors how we expect a single, centralized system to behave. Consider your bank account balance. If you deposit $100, you expect that when you immediately check your balance through your mobile app, an ATM, or online banking, all sources will show your updated balance. If you then withdraw $50, you expect every subsequent check to immediately reflect the new, lower balance. You would be very unhappy if one ATM showed your old balance and another showed the new one. This immediate, universal agreement on the true state of your account is an example of strong consistency in action. How is strong consistency typically achieved in a distributed system? it usually involves significant coordination. Synchronous replication. When data is written, the system waits for all or a majority of the replicas, copies, across different nodes to acknowledge that they have successfully stored the data before confirming the write as complete to the user. This ensures that when the write operation returns success, the data is indeed durable and accessible from multiple locations. Distributed transactions. Mechanisms like two-phase commit, 2PC protocols ensure that an operation involving multiple nodes either successfully completes on all participating nodes or rolls back on all of them. This is crucial for maintaining data integrity across distributed databases. The analogy here is a single, authoritative ledger in a physical bank. Every deposit and withdrawal must be immediately recorded in this one ledger, and everyone, every teller, every ATM, every online portal must consult this single, definitive source of truth to provide your balance. There are no competing versions of your balance. 3.3 The price of perfection, latency and performance. While strong consistency offers the most intuitive and reassuring data model, it comes with significant trade-offs, especially in a distributed environment. Increased latency for writes. Achieving strong consistency often means paying a performance penalty. For a write operation to be considered successful, it typically needs to propagate and be acknowledged by multiple nodes replicas, often spanning different geographical locations. This process adds network round-trip times and processing delays, meaning write operations take longer to complete. If our bank ledger requires every teller in every branch across the globe to physically confirm an update before it's official, transactions would be extremely slow. Reduced availability. This is where the core of the CAP theorem begins to manifest. If a system demands strong consistency, what happens when a node or a network link fails? If the system cannot communicate with all necessary replicas to guarantee that a write has been universally consistent, it often has to throw an error or reject the write altogether. This means that if a part of the system becomes unreachable, a network partition, the system cannot provide a consistent view, and thus it forfeits availability for that particular operation or data. It simply cannot respond until consistency can be reestablished. Complexity. Implementing and managing strong consistency across a diverse and failure-prone distributed network is technically challenging and requires sophisticated synchronization mechanisms that add overhead to the system. In essence, strong consistency forces the system to prioritize data accuracy and global agreement over responsiveness during periods of network instability. It's like trying to get 10 people in different soundproof rooms to simultaneously and instantly agree on the exact wording of a sentence. This requires constant, synchronous communication, and if one room loses power, the whole process grinds to a halt to ensure no one speaks out of turn. 3.4 When consistency matters most. Despite the challenges, strong consistency is not always optional. There are critical scenarios where the cost of inconsistency outweighs the benefits of high availability or performance. Financial transactions. As illustrated with the bank account balance, monetary values absolutely must be strongly consistent. Debiting an account and crediting another must be a single, atomic operation, ensuring no money is lost or created out of thin air. Unique identifiers. When creating a new user account, a social media handle, or a product ID, it's imperative that these identifiers are truly unique. If a system allows two users to register the same username due to a temporary inconsistency, it leads to a catastrophic user experience and data corruption. Critical system state. In systems like command and control, or those managing critical infrastructure, e.g., power grids, air traffic control, maintaining a globally consistent view of the system's operational state is paramount. Incorrect or stale information could lead to dangerous outcomes. Voting systems. When tallying votes, every node must agree on the absolute, true count to ensure fair and accurate results. These are areas where data accuracy and agreement are so critical that any compromise could have severe consequences. For such applications, designers often choose to sacrifice some availability during network partitions to uphold strict consistency requirements. 3.5 The seeds of compromise. where consistency begins to bend, while strong consistency provides a powerful and reassuring guarantee. Its demanding requirements often lead to performance bottlenecks and reduced availability in the face of inevitable network failures. For many applications, particularly those driven by massive scale and continuous user interaction, a degree of eventual looseness, inconsistency, becomes not only acceptable but even necessary. This leads us to the idea that perhaps not all data needs to be immediately and universally consistent. What if, for certain types of data, it's okay for different parts of the system to have slightly different versions for a short period, as long as they eventually converge? This thought introduces the spectrum of consistency models, moving beyond the gold standard of strong consistency towards models like eventual consistency. We'll explore these alternative approaches in a later chapter, but for now, it's important to understand that the choice of consistency is a fundamental design decision, often dictated by the specific needs and tolerance for error of a given application. Next, we'll explore the second leg of the CAP theorem, availability. What does it mean for a distributed system to be always on, and how do these principles interact and sometimes clash? Chapter 4, Availability. Always on, always ready. In the previous chapter, we explored consistency, C, as the demand that every user sees the same, most up-to-date data. Now, let's turn our attention to the second pillar of the CAP theorem, availability. While consistency ensures data integrity, availability, A, is about accessibility and responsiveness. 4.1 What do we mean by available? In the context of the CAP theorem, availability means that every non-failing node in the system must be able to process requests and provide a response, even if some other nodes have failed or are unreachable. It is essentially the guarantee that the system, or parts of it, remains usable and responsive with minimal downtime or interruption. Think of it this way: if you try to access a website, you expect it to load. If you try to log into your email, you expect to get a response, whether it's a success message or an error, within a reasonable timeframe. The system doesn't just hang or leave you staring at a spinning wheel. A highly available system is one that can continue to operate and serve user requests even when individual components or connections within the system fail. It prioritizes responsiveness above all else. If you email a friend, you expect the email service to accept your message, even if it might take a moment for your friend's inbox to register it. You don't want the service to tell you, "Sorry, we can't accept your email because we're currently trying to synchronize some internal data." 4.2 The demand for constant uptime. In today's digital world, users and businesses alike have a near-zero tolerance for downtime. Services like social media platforms, e-commerce sites, and cloud storage providers are expected to be always on. Even a few minutes of downtime can lead to significant financial losses, reputational damage, and frustrated users. This demand for constant uptime has driven the design of distributed systems towards extreme levels of availability. Techniques used to achieve high availability include redundancy. Every critical component, server, database, network link has at least one backup. If the primary component fails, the system automatically switches to the backup. This is like having spare parts ready or understudies for every role in the orchestra. If one musician can't perform, another immediately steps in. Automatic failover. When a component fails, the system automatically detects the failure and reroutes traffic or operations to healthy components without human intervention. Load balancing. Incoming requests are distributed evenly across multiple servers, preventing any single server from becoming overwhelmed and ensuring efficient use of resources. This also helps during failures, as traffic can be directed away from struggling servers. Geographic distribution, deploying services across multiple data centers in different regions. If an entire data center goes offline, e.g., due to a power outage or natural disaster, traffic can be rerouted to another data center far away. Consider a social media platform like Twitter. When you try to post a tweet or refresh your feed, you expect an immediate response. If one of their thousands of servers crashes, you wouldn't expect the entire service to go down. Instead, the highly available design ensures that your request is simply handled by another healthy server. you might not even notice the underlying failure. This relentless pursuit of uptime provides a seamless user experience, making the complex underlying failures largely invisible. 4.3 The cost of being always on, the potential for stale data. While high availability is a highly desirable trait, it comes with its own set of trade-offs, particularly when contrasted with strong consistency. The core tension arises when a network partition occurs, a topic we will deep dive into in the next chapter. If a system prioritizes availability during a network partition, it will choose to continue serving requests even if it cannot communicate with all other parts of the system to verify the absolute latest data. This means response with potentially stale data. If a part of the system is isolated, it might serve data that is not the absolute latest version because it cannot reach the primary source or other replicas to confirm. For example, if a user updates their profile picture and then immediately tries to view it from a server on the other side of a network partition, that server might still show the old picture because it hasn't received the update yet. It prioritizes responding, availability, over guaranteeing the most recent state consistency. Accepting writes without global confirmation. Similarly, a system prioritizing availability might accept new writes even if it can't guarantee that all replicas have received them. It will process the request and respond to the user, hoping that the data will eventually reconcile once the network partition is resolved. This is often referred to as optimistic updates. The critical point here is that maintaining availability in the face of network partitions means that the system is willing to deliver a response, even if that response might not reflect the most recent global state of the data. It's a pragmatic choice. Better to give a slightly out-of-date answer than no answer at all. 4.4 When availability matters most. There are many scenarios where availability is the highest priority, even at the cost of some temporary inconsistency. Social media feeds. If you miss a tweet or a post immediately, it's usually not critical. Your feed might show an older version for a few seconds or minutes, but you'll eventually see the latest content. The ability to always load your feed, even if it's not perfectly up to the second, is more important than perfect consistency. E-commerce browsing. When you browse products on an online store, it's far more important that the product pages load than that every single item's stock count is perfectly accurate at that split second, unless you're trying to purchase the last item. If the system became unavailable every time a stock change occurred, the entire shopping experience would grind to a halt. Caching systems, content delivery networks, CDNs, and caching layers prioritize serving content quickly. They often store copies of web pages, images, and videos. While this cached content might occasionally be slightly out of date, the speed at which it can be delivered far outweighs the need for absolute real-time consistency. Messaging systems. When sending an instant message, you expect the message to be accepted immediately, even if it takes a moment to reach the recipient's device, or if your message history is not perfectly synchronized across all your devices for a brief period. The ability to send is paramount. In these systems, users tolerate occasional eventual consistency because the benefit of always being able to interact with the service outweighs the need for instantaneous, perfect data synchronization. The user experience is paramount, and a system that is consistently available provides that. 4.5 The inevitable face-off. Consistency versus availability. The concepts of strong consistency and high availability stand in direct opposition when a network partition occurs. If a system is partitioned and a client tries to write data to one side of the partition, how should the system respond? If it prioritizes consistency, it will refuse the write or read because it cannot guarantee that the operation can be consistently applied across the entire system. This means it becomes unavailable during the partition. If it prioritizes availability, it will accept the write or serve the read, but it cannot guarantee that all parts of the system are updated or reflect the true global state. This means it becomes inconsistent during the partition. This fundamental tension is the crux of the CAP theorem. It's not about which is better, but about choosing which one is most appropriate for your specific application when faced with the unavoidable reality of network failures. In the next chapter, we will directly confront this concept of partition tolerance and explore how these network failures force the difficult choice between consistency and availability. Chapter 5: Partition Tolerance. Surviving the Digital Divide. We've explored consistency, C, the demand for universal, up-to-date data and availability, A, the commitment to keeping the system responsive. Now we arrive at the third, and arguably most crucial, leg of the CAP theorem, partition tolerance. This is the unavoidable reality that forces the choice between C and A. 5.1. What do we mean by partition tolerance? In the context of the CAP theorem, partition tolerance, P, signifies that the distributed system continues to operate despite arbitrary message loss or failure of parts of the system. More specifically, it refers to the ability of a distributed system to continue functioning even if there is a network partition. A situation where communication between nodes or subsets of nodes is disrupted. Imagine our distributed system as a city with various districts, nodes or groups of nodes, connected by roads, network links. A network partition is like a section of the city being hit by a major earthquake or a power outage, severing all roads and communication lines to other parts of the city. The districts are now isolated. They can still operate internally, but they cannot send messages to or receive messages from the isolated districts. This isn't just about a node crashing. A node crash is a failure, and a well-designed system can often route around it or have a replica take over. A partition is different. It means that the network itself has failed to deliver messages between groups of healthy nodes. The nodes on either side of the partition are working fine in isolation, but they cannot communicate with each other. This digital divide can arise from various real-world scenarios. Network cable cuts. A physical cable is damaged or cut. Router or switch failures. A critical networking device malfunctions. Geographic disasters. An entire data center loses connectivity due to a natural disaster. Software glitches. Bugs in network protocols or operating systems can cause nodes to erroneously believe others are unreachable. Overloaded networks. Severe network congestion can make communication so slow that it's effectively a partition. Messages are delayed indefinitely or dropped. The key insight is that network partitions are not if but when. In any sufficiently large and complex distributed system, particularly those spanning wide geographical areas, network issues are an inevitable part of life. You cannot design a system that guarantees 100% reliable network communication at all times. Therefore, the ability to tolerate these partitions is practically a requirement for any real-world distributed system. 5.2. The inevitable necessity of partition tolerance. Why is partition tolerance so often considered a mandatory property for modern distributed systems? Distributed nature. By definition, a distributed system involves multiple nodes communicating over a network. If that network link breaks, the nodes are partitioned. Unreliable networks. As discussed in Chapter 2, networks are inherently unreliable. They are prone to latency, packet loss, and outright disconnections. It is virtually impossible to build a large-scale distributed system without encountering these issues. Scale. As systems grow larger, with more nodes and wider geographical distribution, the probability of some part of the network experiencing a partition at any given time increases significantly. Operational resilience. Organizations want their services to continue operating even when components fail. Waiting for a network repair for every minor glitch is unacceptable for modern applications. Given that network partitions will occur, a system must decide how to behave when it finds itself in such a state. This is where the CAP theorem really hits home. 5.3. The CAP theorem. The impossible triangle explained. Eric Brewer's CAP theorem explicitly states that in the presence of a network partition, P, a distributed system must choose between guaranteeing consistency, C, or guaranteeing availability, A. It cannot guarantee both. Let's break down why this choice is forced. Suppose your distributed system has two nodes, Node 1 and Node 2, storing a piece of data, let's say, your bank balance. Initially, both nodes agree that your balance is $100. Now, a network partition P occurs. Node 1 and Node 2 can no longer communicate with each other. They are isolated. Scenario A. Choose consistency over availability, CP system. A client requests to withdraw $50 from Node 1. Node 1 receives the request and updates its local balance to $50. Problem. Node 1 must ensure that this update is reflected on Node 2 to guarantee strong consistency. But because of the partition, Node 1 cannot communicate with Node 2. CAPS force. To maintain consistency, Node 1 has two options. Refuse the write. Node 1 sends an error message back to the client saying it cannot complete the transaction because it cannot guarantee the consistency of the data across the entire system. Refuse the read if data is uncertain. If a client tries to read data from Node 1 and Node 1 isn't sure if it has the very latest version, because it can't talk to Node 2, which might have received a later update, Node 1 might refuse the read. Result. The system becomes unavailable during the partition to guarantee consistency. It chooses to halt operations rather than risk propagating inconsistent data. This is typically the behavior of traditional relational databases that strive for strong consistency, e.g., PostgreSQL or MySQL clusters often become unavailable in a partition if they cannot maintain their strict consistency guarantees. Scenario B. Choose availability over consistency, AP system. A client requests to withdraw $50 from Node 1. Node 1 receives the request, updates its local balance to $50, and responds to the client that the transaction was successful. Simultaneously, another client requests to check the balance from Node 2. Node 2, unaware of the update on Node 1 due to the partition, still reports the balance as $100. Problem. The system has now provided two different, conflicting views of the same data at the same time. It is inconsistent. CAPS force. To maintain availability, Node 1 proceeds with the operation even though it cannot confirm consistency with Node 2. Result. The system remains available during the partition, but it forfeits strong consistency. It prioritizes responding to requests over guaranteeing that all data is immediately synchronized. This is typical for many modern NoSQL databases and large-scale distributed systems designed for high availability, e.g., Apache Cassandra, many cloud storage services. Once the network partition is resolved, these systems then work to reconcile the discrepancies, a process often called eventual consistency, which we will discuss later. The key takeaway is that the CAP theorem tells us that P is almost always a given. In real-world distributed systems, network partitions will asterisk happen. Therefore, the choice between C and A becomes a mandatory design decision, a fundamental trade-off. You decide whether your system will temporarily halt operations, sacrificing A to ensure everyone sees the same data, C, or if it will keep operating, maintaining A, even if it means some people see different, potentially stale data, sacrificing C. The brilliance of the CAP theorem lies not in declaring an outright impossibility, but in providing a clear framework for understanding the hard choices that engineers must make when developing distributed systems. It's a tool for thinking about trade-offs, not a barrier to progress. In the next chapter, we will delve deeper into specific examples of systems that have made these choices, illustrating how their design reflects their commitment to either consistency or availability when faced with the unavoidable reality of network partitions. Chapter 6, the CAP Theorem, the impossible triangle explained. By now, you've met the three powerful forces at play in distributed systems: consistency, C, availability, A, and partition tolerance, P. You understand that consistency dictates that all data views must be the same and up to date. You know that availability ensures the system is always responsive. And you've seen that partition tolerance acknowledges the inevitable reality of network failures, segmenting our system. Now, we bring them all together to fully explain the core assertion of the CAP theorem. In a distributed system, you can only ever practically guarantee two out of these three properties when a network partition occurs. 6.1 The core problem. Network partitions are unavoidable. Let's reiterate the critical premise that underpins the CAP theorem. Network partitions are an unavoidable reality in large-scale distributed systems. This isn't a theoretical what if. It's a when for any system of significant size or geographical distribution. Why are partitions so prevalent? Real-world unreliable networks. The internet and large-scale data center networks are complex beasts. Routers fail, cables are cut, congestion occurs, configurations get messed up. These aren't minor hiccups. They can effectively sever communication between entire groups of servers. Geographical distribution. When your data processing spans multiple continents, the sheer physical distance and the number of interconnected devices increase the probability of a communication breakdown between different regions. Partial failures. As discussed, distributed systems live in a world of partial failure. A node might slow down, drop packets, or behave eccentrically, mimicking a partition even if the underlying network is otherwise sound. Because you cannot opt out of partitions, partition tolerance, P, is almost always a non-negotiable requirement for any useful distributed system. If your system couldn't tolerate partitions, any network hiccup would bring the entire system to a halt, rendering it useless in a real-world scenario. Therefore, in practical terms, you are always building a P system. This fundamental requirement, that your system must be able to withstand network partitions, forces a choice. Since P is a given, you must then choose between C and A, 6.2 the forced choice. CP versus AP systems. The CAP theorem is often visualized as a triangle, where you can pick any two corners, but never all three. Since P is implicitly chosen because networks will partition, the practical dilemma becomes C or A? Let's revisit our conceptual two-node system, Node 1 and Node 2, storing a bank balance, initially $100. Scenario: a network partition occurs. Node 1 and Node 2 lose the ability to communicate with each other. Option 1, prioritize consistency, CP system. Choice: if we prioritize consistency, C, it means we demand that all clients always see the most recent, unified view of the data. Behavior during partition. A client interacts with Node 1 and tries to deposit $50. Node 1 updates its local balance to $150. Crucially, to guarantee consistency, Node 1 must ensure this update is also committed by Node 2. Because Node 1 cannot communicate with Node 2 due to the partition, it faces a dilemma. It cannot confirm that Node 2 has the latest data. To prevent inconsistent states, Node 1 will refuse to complete the right operation. It will send an error message back to the client, or simply hang until the partition heals. Similarly, if a client tries to read data from Node 2 cannot be sure if Node 1 has a more recent update. To maintain consistency, Node 2 may also refuse to serve the read or return an error. Outcome: the system sacrifices availability, A, during the partition. While parts of the system are technically up, they are not responsive to new requests that would compromise the consistent view of data across the entire system. You get reliability in data, but not continuous operation. Analogy: imagine two separated accounting offices, each with a copy of a company's ledger. A new transaction comes in, but the offices can't communicate. If they prioritize consistency, they will refuse to record the new transaction until they can verify it with the other office and ensure both ledgers are identical after the update. This means, during the communication breakdown, you cannot perform new transactions, making you unavailable for business, but ensuring your books are always accurate. Option 2, prioritize availability, AP system. Choice: if we prioritize availability, A, it means we demand that the system remains responsive to client requests, even if it cannot guarantee globally consistent data at that exact moment. Behavior during partition. A client interacts with Node 1 and tries to deposit $50. Node 1 updates its local balance to $150 and successfully responds to the client, confirming the deposit. At the same time, another client interacts with Node 2 and tries to withdraw $20. Node 2, unaware of the deposit on Node 1, due to the partition, might still show the balance as $100 and allow the withdrawal, leading to a balance of $80 on Node 2's ledger. Outcome: the system sacrifices strong consistency, C, during the partition. It remains responsive and accepts operations, but different parts of the system might present conflicting views of the data. Data reconciliation will need to happen once the network partition heals. Analogy: using the same accounting offices, if they prioritize availability, they will continue to process new transactions independently, even if they can't cross-verify with the other office. This means business continues uninterrupted, available, but the two ledgers might now show different balances, inconsistent. This divergence will need to be resolved later when communication resumes. 6.3. What the CAP theorem doesn't say. It's just as important to understand what the CAP theorem doesn't say. It doesn't say you can never have consistency and availability simultaneously. You absolutely can, as long as there is no network partition. The theorem only applies in the presence of a P. If your network connection is perfect, your system can be both C and A. It doesn't say which choice is better. The best choice, CP or AP, is entirely dependent on the specific requirements of your application. For banking transactions, you almost certainly need CP. For a social media feed, AP is usually preferred. It doesn't specify the type of consistency. CAP typically refers to strong consistency, linearizability, or atomicity. It doesn't preclude weaker forms of consistency, like eventual consistency, which are often leveraged by AP systems. It doesn't recommend abandoning any property entirely. Even a system choosing AP will still strive for some level of consistency, eventual consistency, and a CP system won't completely abandon availability. It's about which property you sacrifice during a partition. 6.4 Practical implications. The designer's dilemma. The CAP theorem forces system designers to make a conscious, fundamental decision about their priorities. If your application cannot tolerate any data inconsistencies, e.g., financial systems, user authentication databases, you must design a CP system. This means you are willing to accept periods of unavailability during network partitions to ensure data correctness. If your application absolutely must remain operational and responsive, even if it means serving slightly stale data temporarily, e.g., social media feeds, online gaming, media streaming, you must design an AP system. This means accepting that data might temporarily diverge during network partitions, with reconciliation happening later. The choice is a reflection of your application's risk tolerance and what it values most: ironclad data integrity at all times or continuous service. Understanding this trade-off is the first step towards building resilient and practical distributed systems. Next, we will explore real-world examples of popular distributed systems and see how they've made their CAP choices. Chapter 7. Choosing two real-world CAP implementations. The CAP theorem is not just an academic curiosity. It's a foundational principle that guides the design choices of virtually every large-scale distributed system you interact with daily. Every popular database, messaging queue, or distributed file system has explicitly or implicitly chosen two properties over the third, especially when faced with the inevitable network partition. Let's examine some prominent examples to see how different systems embody CP or AP strategies. 7.1 Prioritizing consistency and partition tolerance. CP systems. Systems that fall into the CP category choose to sacrifice availability. A. During a network partition to ensure strong consistency. C. Across all data and partition tolerance. P. When a partition occurs, if a node cannot confirm synchronous communication with its peers to guarantee the latest, globally agreed-upon state, it will refuse to process requests that could lead to an inconsistent state. This means it becomes unavailable for those operations. Traditional relational databases with clustering, e.g., MySQL with master-slave replication, PostgreSQL with synchronous replication, while single-instance relational databases are inherently C, as there's no distribution. When you cluster them for high availability and scale, the CAP theorem becomes relevant. Many traditional RDBMS deployments can be configured to favor CP. How they work: data is replicated across multiple servers. If synchronous replication is chosen, a write operation isn't considered complete until it's acknowledged by all or a quorum of replicas. CAP choice: If a network partition occurs and the primary database can't communicate with its replicas or its quorum, it will often stop accepting writes and sometimes reads to prevent data divergence. Example: imagine a bank using a synchronously replicated database. If the network between two data centers fails, the system might refuse to process new transactions until the connection is restored or a clear majority of nodes can be established. This ensures that every customer always sees the correct balance, but at the cost of service interruption during severe network issues. Trade-off: high data integrity for critical financial or state data. The cost is potential downtime during network partitions. Zookeeper, etc. console. These are not databases in the traditional sense, but distributed coordination services. They are central to many distributed systems for managing configuration, naming, providing distributed synchronization, and maintaining group services. Their primary goal is to ensure that every client sees the exact same system state at all times. How they work: they use consensus algorithms like ZAB for Zookeeper, Raft for etc. that require a strict majority, a quorum of nodes to agree on any update before it's committed. CAP choice: they are CP systems. If a network partition occurs such that a quorum cannot be formed by the majority of servers, the minority partition will effectively become unavailable for writes, and often reads that seek the latest state. Example: if Zookeeper manages the configuration for an application and its cluster partitions, the application might be unable to update its configuration until Zookeeper can re-establish its quorum. This prioritizes the correctness of the configuration data over its continuous availability during a severe network split. Trade-off: essential for critical metadata and distributed state coordination, where even minor inconsistencies could lead to system chaos. Relies on strict consensus to maintain consistency, which halts operations if consensus cannot be achieved due to partitions. 7.2 Prioritizing availability and partition tolerance. AP systems. AP systems prioritize continuous operation, availability, and the ability to survive network partitions, partition tolerance, by allowing for temporary inconsistencies, sacrificing strong consistency. When a partition occurs, nodes continue to process requests, even if they can't communicate with other nodes to ensure global consistency. These systems typically employ eventual consistency models, meaning that data will eventually converge once the network partition heals. Apache Cassandra, a popular NoSQL distributed database system renowned for its high availability and scalability. How it works: Cassandra allows clients to read and write data to any node in the cluster. It employs a tunable consistency model, but its default and most common configurations lean heavily towards AP. Data is replicated, and clients can specify how many nodes must acknowledge a write or respond to a read, quorum settings. CAP choice: in the face of a network partition, Cassandra will continue to accept reads and writes on both sides of the partition. This means it prioritizes availability. If conflicting writes occur during a partition, they are resolved later using techniques like last write wins or application-defined conflict resolution, leading to eventual consistency. Example: Facebook's inbox search, an early, large user of Cassandra, used this model. It was more important that you could search your inbox, even if the results weren't perfectly up-to-the-second accurate in a high-contention, partition scenario, than it was for the search to fail completely. Trade-off: exceptional uptime and scalability. The cost is that, during a partition, different clients might temporarily see different versions of the data, and conflicts might need to be resolved. DynamoDB, and inspired systems like Ryuk, Couchbase. Amazon's highly available, scalable NoSQL database service, heavily influenced by its internal Dynamo paper. How it works: DynamoDB is a distributed key-value store designed from the ground up for high availability. Data is replicated across multiple nodes and availability zones. CAP choice: it is fundamentally an AP system. It guarantees that write operations will eventually be propagated to all replicas, but not necessarily immediately. During a partition, it will allow operations to continue, aiming to serve responses even if some replicas are unreachable. clients might read stale data. Example, an e-commerce shopping cart. It's better for a user to be able to add an item to their cart, availability, even if, for a brief moment, their cart content isn't perfectly consistent across all replicas. Once the network heals, the carts will synchronize. Trade-off, extremely high availability and resilience to network failures. The cost is that data might be eventually consistent, meaning it will eventually converge, but there might be a period where different clients see different data. 7.3 The nuance. It's not always black and white. While the CAP theorem forces a choice between C and A in the face of P, it's important to understand that. It's often a spectrum, not a binary choice. Systems that lean toward AP still offer configurable levels of consistency. You can often choose to require more replicas to acknowledge a write, making it more consistent, but potentially less available, or less, making it more available, but less consistent. Consistency models vary. There are many types of consistency, weaker than strict strong consistency, that are very useful, e.g., eventual consistency, causal consistency, read your writes. AP systems often rely on these. Different parts of a system can make different CAP choices. A complex application might use a CP service, like Zookeeper, for critical configuration data, while using an AP database, like Cassandra, for user profiles or feed data, intelligently choosing the best fit for each component. The P is assumed. For almost all practical distributed systems running on real-world networks, the P is simply a given. The question then simplifies to, will your system prioritize availability or consistency when the network inevitably breaks down? The choice between CP and AP is one of the most critical design decisions for any distributed system architect. It directly impacts the system's behavior during outages, its performance characteristics, and ultimately, the user experience. By understanding these real-world implementations, you can begin to appreciate the practical trade-offs involved and how different companies have balanced these fundamental properties to meet their specific business needs. The next chapter will delve into the practical strategies and thought processes behind making these crucial CAP-inspired design choices. Chapter 8, Designing for CAP, Practical Strategies and Trade-offs. Understanding the CAP theorem isn't merely an academic exercise. It's a crucial guide for making informed design decisions when building distributed systems. Since partition tolerance, P, is an unavoidable reality in any non-trivial distributed system, your primary focus shifts to thoughtfully choosing between consistency, C, and availability, A. This chapter explores how real-world systems navigate this choice and offers practical strategies. 8.1 Embracing the trade-off. No silver bullet. The first and most important strategy is to accept the CAP theorem for what it is, a fundamental constraint. There is no silver bullet that allows you to have perfect consistency and perfect availability simultaneously in the face of a network partition. Once you embrace this truth, you can start making deliberate choices based on your application's specific needs. Ask yourself these questions. What is the cost of inconsistency? For financial transactions, it's catastrophic. For a social media, like Count, it might be trivial or acceptable for a brief period. What is the cost of unavailability? For an e-commerce website during Black Friday, even minutes of downtime mean millions in lost revenue. For an internal analytics dashboard, it might be acceptable for a few hours. How frequently do partitions occur, and for how long? While partitions are inevitable, their frequency and duration can influence the severity of the trade-off. The answers to these questions will guide your system's CAP leanings. 8.2 CP-oriented strategies. Prioritizing consistency. When strong consistency is paramount, you design your system to prioritize C over A during a partition. The goal is to ensure that data is never conflicting, even if it means users occasionally see error messages or experience a temporary halt in service. Strategies for CP systems. Quorum-based consensus. Concept. For any write operation, a majority or a defined quorum of nodes must agree and acknowledge the write before it's considered successful. For a read, a quorum of nodes must respond, ensuring you get the most up-to-date version. How it works. If a network partition occurs and a node cannot reach its quorum, it will refuse to process the request. This ensures that no writes are committed or reads served if the system cannot guarantee a globally consistent view of the data. Example, distributed agreement protocols like Paxos, used by Google's Chubby, Apache Zookeeper, and Raft, used by Etcetera console, are designed to achieve strong consistency using quorums. These are ideal for managing critical metadata, distributed locks, or leader election. Trade-off: strong consistency, but susceptible to unavailability if a quorum cannot be formed due to network issues or node failures. Strict transactional semantics, distributed transactions. Concept: operations across multiple nodes are treated as atomic transactions. Either all parts of the transaction succeed or all fail, ensuring a consistent state. How it works: protocols like two-phase commit, 2PC, are used to coordinate transactions across distributed databases. If any participant in the transaction fails or becomes unreachable, the entire transaction is rolled back or aborted. Example, ensuring money transfer from account A to account B across different bank databases. If communication with account B's database fails, the entire transfer is canceled or held in escrow. Trade-off: guarantees atomicity and isolation, but can be slow and deadlock-prone, drastically impacting performance and availability in large, failure-prone systems. Fail fast, fail safe. Concept: when in doubt about consistency, the system chooses to err on the side of caution and abort the operation. How it works: rather than risking an inconsistent state by continuing during a partition, the system explicitly returns an error or becomes unresponsive. Users are immediately aware of a problem rather than operating on potentially stale data. Consideration: requires robust error handling on the client side to deal with these periods of unavailability. 8.3 AP-oriented strategies. Prioritizing availability. When continuous operation is more critical than instantaneous consistency across the entire system, you design your system to prioritize over C during a partition. The goal is to keep serving requests and accept writes, even if it means dealing with conflicts and data eventual convergence later. Strategies for AP systems. Eventual consistency. Concept: after a write, the system eventually propagates updates to all replicas, but there's no guarantee that all reads will see the latest write immediately. All replicas will eventually converge to the same state. How it works: during a partition, any available node accepts writes. When the partition heals, reconciliation mechanisms run in the background to resolve conflicts, e.g., last write wins, merging strategies, or application-specific logic. Example, many NoSQL databases like Cassandra and Amazon DynamoDB natively support eventual consistency. Social media news feeds or IoT sensor data are often strong candidates for this model. Trade-off: high availability and scalability, but requires careful handling of stale data and potential conflicts by the application. Conflict resolution. Concept: since AP systems allow for temporary inconsistencies, strategies are needed to resolve conflicts that arise when partitions heal and divergent data needs to be merged. How it works: last write wins, LWW. Simple but can lead to data loss. The update with the latest timestamp is considered the winner. Data merging: custom logic to merge conflicting data, e.g., for a document merging different edits. Version vectors: more complex mechanisms to track the history of changes and determine which changes need to be applied. Consideration: developers need to design for and implement these resolution strategies, which can add complexity to the application logic. Relaxed consistency guarantees tunable consistency. Concept: some AP systems allow users to tune the consistency level for each read or write operation. How it works: you can specify requirements like read from any one replica, low consistency, high availability versus read from a quorum of replicas, higher consistency, lower availability. Example: Cassandra's consistency levels allow you to choose how many replicas must acknowledge a write or respond to a read. Trade-off: provides flexibility, but requires designers to deeply understand consistency models and their implications for different types of data within their application. 8.4. Hybrid approaches and microservices. It's rare for an entire large-scale application to be purely CP or AP. Modern systems often adopt a hybrid approach, using different CAP models for different services or data sets based on their individual requirements. Microservices architecture. Break down a large application into smaller, independent services. Each service can then make its own CAP choice. For instance, an order processing service might be CP due to the critical nature of financial transactions, while a product recommendation service might be AP because occasional stale recommendations are acceptable. Read your rights consistency. A user might submit a post. While it may take time to propagate across the system, eventual consistency, the system might guarantee that that specific user will always see their own latest post immediately. This provides a user-centric strong consistency guarantee without requiring global strong consistency. Separation of concerns. Distinct data types might have different consistency requirements. Critical ledger data needs strong consistency, while log data can be eventually consistent. 8.5. The journey is the design. Designing for CAP is a continuous process of understanding your system's data, its failure modes, and the tolerance levels of your users and business. It's about making conscious decisions about trade-offs, documenting them, and building systems that are robust and predictable in the face of the messy realities of distributed computing. The CAP theorem doesn't give you the answer, but it gives you the fundamental question to ask. As we move forward, we'll see that while the CAP theorem defines the boundaries, the landscape within those boundaries is rich with various approaches to consistency, many of which aim to provide practical compromises while leaning towards high availability. That leads us to the next chapter, exploring models like eventual consistency that often serve as the backbone for highly performant and available distributed systems. Chapter 9. Beyond CAP. Eventual consistency and modern approaches. By now, you understand the fundamental dilemma posed by the CAP theorem. When a network partition, P, strikes, you must choose between consistency, C, and availability, A. For many modern, large-scale systems, particularly those demanding high uptime and massive scalability that rely on distributed architectures, the choice often leans towards availability. This means they are willing to relax the strongest form of consistency in favor of being always on. This is where the concept of eventual consistency becomes vital. 9.1. Eventual consistency. The practical compromise. Eventual consistency is a consistency model that offers a pragmatic middle ground, especially for systems that prioritize availability, A, over strong consistency, C, during partitions. The definition. Eventual consistency guarantees that, if no new updates are made to a given data item, eventually all accesses to that item will return the last updated value. The idea. Data changes propagate through the system over time. There might be a temporary period where different replicas of the same data hold different values. However, given enough time, and assuming all network issues resolve, all replicas will converge to the last updated value. Imagine a group of friends chatting across different messaging apps. If one friend sends a message, it might appear instantly on some friends' phones. But due to network delays or app glitches, it might take a few seconds or even minutes for others to receive it. Eventually, everyone sees the message and the conversation is synchronized. That's eventual consistency in action. Why embrace eventual consistency? High availability. Systems can continue to process reads and writes even when some nodes are unreachable or in a partition state. This is crucial for user experience in many applications. Scalability. It reduces the coordination overhead dramatically. Nodes don't need to synchronously agree on every write, freeing them to process requests independently and rapidly. This allows systems to scale horizontally by simply adding more nodes. Performance. Lower latency for writes, as they don't need to wait for acknowledgement from all replicas. Read latency can also be reduced by allowing reads from any available replica. Drawbacks of eventual consistency. The main challenge with eventual consistency is dealing with reads that might return stale data. This is often described as read-after-write consistency issues, where a user writes data but then immediately reads it back and sees an older version. Another challenge is conflict resolution when multiple writes occur to the same data item across different partitions. 9.2 Consistency spectrum. Beyond just strong or eventual. While strong and eventual consistency represent two ends of a spectrum, there are many nuanced consistency models in between. These models try to offer stronger guarantees than pure eventual consistency without the full performance and availability overhead of strong consistency. Some common ones include causal consistency. If one operation causes another, e.g., you post a comment, and then someone replies to that specific comment, then anyone who sees the reply is guaranteed to also see the original comment. However, concurrent, unrelated operations might still be seen out of order. Read your writes consistency. A client is guaranteed to always see its own latest writes. If you update your profile on social media, you will always see your updated profile, even if others might see an older version for a short period. Session consistency. If a user initiates a session, then all subsequent operations within that session are guaranteed to see data consistently, e.g., read your writes monotonic reads. Monotonic reads. If a client reads data, subsequent reads by that same client will never see an older version of the data. They will either see the same version or a newer one. These models allow developers to tailor the consistency guarantee to the specific needs of their application, offering more flexibility than the strict see a dichotomy implied by the CAP theorem in its simplest form. 9.3 Practical approaches and technologies leveraging eventual consistency. Many modern distributed systems successfully leverage eventual consistency and related models to achieve massive scale and high availability. NoSQL databases, e.g., Apache Cassandra, Couchbase, Amazon DynamoDB, Ryuk. These databases are designed to be highly available and partition tolerant. They often allow tunable consistency, where you can configure the level of consistency, e.g., how many nodes need to agree on a write or respond to a read, but default to and excel at eventual consistency. Content Delivery Networks, CDNs. When you request a web page or video, it's often served from a CDN edge location geographically close to you. These edge servers cache content. While a CDN might not have the absolute latest version of every web page, e.g., if a tiny modification was made a few seconds ago, they prioritize delivering some version of the content quickly and reliably. Updates eventually propagate to all edge locations. Distributed caching systems, similar to CDNs, they store copies of data for faster retrieval. Temporary inconsistencies are acceptable for performance gains. Messaging queues, e.g., Apache Kafka. Kafka is highly available and durable, but its consistency model is more nuanced. Producers append messages to logs, and consumers read from these logs. While messages within a partition are ordered, there isn't a global, instantaneous consistency guarantee across all partitions and consumers. They generally prioritize availability and throughput. 9.4 Thinking beyond the CAP theorem. Shifting paradigms. While the CAP theorem correctly identifies the fundamental trade-off, its greatest contribution might be in making designers aware of these unavoidable choices. This awareness has led to several shifts in how complex distributed systems are designed. Focus on recoverability and fault tolerance. Instead of trying to prevent all failures, which is impossible, engineers now design systems that can quickly detect failures, isolate them, and recover gracefully. This involves automated failovers, self-healing mechanisms, and robust monitoring. Explicit conflict resolution. For AP systems, the assumption is that conflicts will happen. The design then shifts to how these conflicts are detected, what strategies are used to resolve them, and whether it's automated or involves human intervention, and what the user experience is like during and after conflict resolution. Application-level consistency. Sometimes, the responsibility for managing consistency is pushed up to the application layer. The database provides a basic level of eventual consistency, and the application code implements specific logic to handle conflicts for its particular domain, e.g., An online game might have specific rules for resolving concurrent moves. Idempotence. Designing operations to be idempotent means that performing the same operation multiple times has the same effect as performing it once. This is crucial in distributed systems where messages might be duplicated due to network retries, ensuring that unintentional multiple executions don't lead to incorrect states. Distributed transactions versus microservices. The complexity and overhead of global distributed transactions, like 2PC, often lead to fragile systems. Modern microservices architectures often favor compensating transactions and eventual consistency across service boundaries, opting for higher availability and scalability. If a multi-step process fails, a compensation action is taken to undo previous successful steps, rather than one giant, synchronous transaction. The CAP theorem is a guiding beacon that illuminates the hard choices. It doesn't tell you how to build your system, but it defines the boundaries within which you must innovate. The journey beyond CAP is about creativity in designing robust, scalable, and user-friendly systems that cleverly navigate these constraints, often by strategically embracing weaker, but more practical consistency models to achieve the overarching goal of continuous service. As we conclude this exploration, remember that understanding the CAP theorem is not an endpoint, but a foundational step. It empowers you to ask the right questions, evaluate architectural choices, and ultimately build distributed systems that truly meet the demands of our interconnected world. Chapter 10, Conclusion, Mastering Distributed Systems. We have journeyed through the intricate landscape of distributed systems, explored the fundamental properties of consistency, availability, and partition tolerance, and grappled with the inescapable choices dictated by the CAP theorem. What began as a seemingly simple academic assertion has revealed itself to be a powerful lens through which to understand and design the complex digital infrastructure that powers our modern world. 10.1. The enduring impact of the CAP theorem. The CAP theorem, first articulated by Eric Brewer, remains as relevant today as it was over 2 decades ago, perhaps even more so. Its enduring impact stems from several key insights. It formalizes an unavoidable trade-off. More than just an observation, it's a mathematical proof that when a network partition occurs, a near certainty in large-scale distributed systems, you simply cannot have perfect consistency and perfect availability simultaneously. This is the bedrock truth on which all distributed systems must be built. It forces conscious design decisions. Before CAP, designers might have inadvertently built systems that tried to achieve all three, leading to unpredictable behavior during failures. Now, architects are empowered to make deliberate, strategic choices, understanding the implications of prioritizing C or A in the face of P. This transparency in trade-offs is invaluable. It explains the diversity of distributed systems, from highly consistent financial ledgers to eventually consistent social media feeds. The CAP theorem clarifies why different systems exist that behave in fundamentally different ways. Their core design is often a direct reflection of their chosen CAP preference. It highlights the importance of partition tolerance. By elevating P to an equal footing, the theorem underscores that network failures are not edge cases but central concerns that must be addressed in any robust distributed system. Ignoring P is akin to building a house without considering earthquakes in a seismic zone. 10.2 From Theory to Practice. Applying the CAP lens. Understanding the CAP theorem is not about memorizing acronyms. It's about developing a mindset. It equips you with the critical thinking necessary to ask the right questions when designing or evaluating any distributed system. What are the core requirements of this specific application? Is data integrity absolutely paramount, or is continuous uptime the overriding goal? What are the consequences of temporary inconsistency versus temporary unavailability? Which is more damaging to the business, the user experience, or the system's overall purpose? How does this system behave during a network partition? Does it stop processing requests? Does it continue, risking stale data? How does it reconcile data once the partition heals? Are there different parts of the system that need different CAP trade-offs? A microservices architecture often allows for this nuanced approach, where each service can pick its optimal consistency model. What are the consistency guarantees for RED operations? Are they strong, eventual, or something in between like read your writes? By applying this CAP lens, you can cut through the marketing hype and deeply understand the architectural compromises made in distributed systems, enabling you to build more resilient, appropriate, and effective solutions. 10.3 The future, ever-evolving challenges. The field of distributed systems is constantly evolving. New architectures, protocols, and technologies emerge regularly, but they all invariably operate within the constraints of the CAP theorem. As we push the boundaries of scale, performance, and geographic distribution, the challenges only become more pronounced. Global distribution. As systems span continents, the inherent latency and increased likelihood of partitions make the CAP choices even starker. Edge computing, moving computation and data closer to the user at the edge, introduces new distributed system challenges where network reliability might be even more tenuous. Real-time demands. Users increasingly expect instantaneous responses and real-time data, pushing the limits of what AP systems can deliver without perceived inconsistencies. AI and machine learning. Deploying and scaling AI models often requires distributed training and inference, where data consistency and model synchronization become critical challenges. These developments don't invalidate the CAP theorem. They highlight its continued relevance as the foundational principle guiding design in increasingly complex environments. Engineers will continue to innovate, devising clever algorithms and architectural patterns to push the boundaries, offering nuanced consistency models, and making the trade-offs more palatable to users. 10.4 Your role, mastering the distributed world. Whether you are a software developer, a system architect, an operations engineer, or simply an inquisitive mind trying to make sense of our digital world, understanding the CAP theorem is a powerful tool. It's not just about a theorem. It's about understanding the fundamental nature of distributed computing, a world where perfect reliability and instant global agreement are illusions, and trade-offs are the currency of success. You've learned that distributed systems are an orchestra of independent components, each a node, connected by the invisible network. You've seen how data is meticulously replicated and communicated, and how partial failures are an expected melody rather than an unexpected discord. You've come to grasp the tension between having everyone play the exact same note at the exact same second, consistency, versus ensuring the music never stops, even if some instruments are briefly out of sync, availability, particularly when the conductor's communications break down, partition. Mastering distributed systems isn't about avoiding these trade-offs, it's about embracing them. It's about designing systems that are robust enough to withstand the inevitable chaos of network failures, while still delivering an exceptional experience to the user. Armed with the insights from the CAP theorem, you are now better equipped to choose your path, navigate the digital divide, and build the next generation of resilient, scalable, and indispensable distributed applications. The unseen orchestra plays on, and now you understand its score.